Good afternoon, everyone. Thank you for joining us today. We're pleased to host you for our presentation, PI Controller Tuning and the Recipe for Success. Whether you tune PID control loops manually or with the help of software, there's a simple, repeatable, and proven procedure that produces successful results. At this time, I ask that you put your phones on mute. If you have questions or comments during today's presentation, please use the WebEx messaging function. We will answer those questions at the conclusion of today's talk during the Q&A portion. My name is Dennis Nash. I'm the president of Control Station. I'm the principal cheerleader of our award-winning monitoring and diagnostic technologies. I'm joined here today by Lindsay Fink, a lead member of our Field Services Engineering team and today's featured presenter. Lindsay joined Control Station in 2014. She holds primary responsibility for building out our field services and support offerings, which are heavily focused on our plant ESP control loop performance monitoring technology. Prior to joining Control Station, Lindsay spent several years in the power sector. She was a senior nuclear engineer with Westinghouse in their nuclear power division. Like many of us here at Control Station, Lindsay received her undergraduate degree from the University of Connecticut, where she majored in chemical engineering. A little bit about Control Station. We simplify process optimization. More specifically, Control Station offers a range of highly intuitive process diagnostic and optimization solutions. Our technologies are private labeled by leading OEMs and supported by a growing network of system integrators and solution partners. We're proud to support the control and optimization needs of world-class manufacturers across the process industries and even around the world. Our value is rooted in simplifying the optimization of PID control networks. Today's session begins with some basics. First, the defining of a control objective, and then a review of dynamic process behavior. Before detailing a repeatable six-step procedure for tuning loops, Lindsay will cover the key attributes of the PID controller, simple steps for calculating model parameters, and considerations for correlations and controller responsiveness. As time permits, we'll be happy to respond to any questions during, again, the Q&A portion of our presentation. So with that, I hand the mic over to Lindsay Fink.
Thank you. So the first step in tuning any loop is to define the control objective. The control objective is specific to a particular loop in a specific facility. So you can imagine that the control objective is subjective, and what's considered good control is the control loop's ability to satisfy that control objective. So for example, some loops you want to reach set point as quickly as possible, and having some overshoot is acceptable. For other loops, it is better to have a nice, smooth, stable response, allowing the controller to take its time reaching set point. So defining a control objective is simple, and there are multiple things that you want to consider when you're defining the control objective. First and foremost, safety is the most important consideration. You want to make sure that you have considered all safety implications related to your loop. Does exceeding a limit release harmful pollutants to the atmosphere? Is there the potential to harm people working in the plant or in the surrounding area? Once you've satisfied the safety implications, there are several other things that you should consider, such as the impact. How does this loop interact with other loops? What is its role in the process, and what are any disturbances that could be affecting the loop? You also want to take into account the management requirements and how management would like to see the loop perform. You want to make sure that you're either able to achieve the management considerations or be able to explain why achieving the management goals is not possible. You also want to consider the economic factors associated with that loop. Is the loop controlling the flow of an expensive raw material into a process, and is there substantial impact on the financials of that loop? You want to consider longevity. You want to keep the control and the control strategy simple. The more simple the controller, the more robust the process, the longer any changes to the control strategy and tuning parameter will stay in place. And finally, equipment. Process equipment is expensive. So you want to make sure that you're understanding how the equipment is being affected by the control of the process. It's important to consider whether the final control element, whether it's a valve or a pump or whatever mechanical component, is being moved and how much effort it's exerting to control the process. You want to work to find tunings that will achieve the control objective while minimizing the wear and tear on the final control element. So when you're determining your control objective and the design level of operation, there are two main considerations. First, you want to determine the normal or expected operating range of your process variable. This is where you expect the loop to operate under normal conditions. Next, you want to consider any typical disturbances that could be affecting your loop. A disturbance is anything outside of the final control element that is impacting your process variable. For example, a disturbance would be if there are multiple lines drawing off of a common header that could be affecting the steam pressure. It's important to establish your design level of operation because loops behave differently under different conditions. So a loop should be designed and tuned for the conditions at which you expect it to actually operate. Here are some examples to illustrate how the control objective is different in different applications. In the first example, we have a temperature controller where the control objective is to maintain very tight control of the temperature, allowing it to vary only plus or minus 0.5 degrees. During set point changes, tight control is also desired and overshoot should be kept to less than 1 degree. And finally, the normal operating range is very specific at 92 degrees Celsius. You can see how the control objective is much different for our second example, the level controller. In this example, the main objective is to prevent the tank from overflowing or emptying. So then it's okay to let the level wander between 35 to 65%. So we're having a much larger range of operation with the main goal being to minimize adjustments to the outflow. So you can see how the control objective for the level is much different than that of the temperature. And finally, in our last example, the flow controller, the main objective here is to have a very quick responding controller, and some overshoot, 4 to 5%, is acceptable. We also have a range of operation where the flow could be anywhere between 75 and 100 gallons per minute. So the dynamic behavior is defined as how the process variable responds over time to changes in the controller output and disturbances. In order to properly tune a controller, you must understand the dynamics of the process. Consider the cruise control system for a car versus a truck. Specifically think about how quickly each vehicle can accelerate or decelerate using the gas pedal. The car is going to respond much more quickly to the gas pedal being pushed down than the truck. Also consider the effect of the disturbances on each vehicle, such as wind, hills, or another vehicle passing by. Again, the car is going to give a much quicker response to any disturbances that could impact the process. So the actions that a properly designed controller must take to control the car versus the truck, that is, how the controller output signal should manipulate gas flow to maintain a constant speed in spite of any disturbances, will differ because the dynamic behavior of the vehicle or process is different. It is also important to know whether the process you are tuning is self-regulating or integrating. A self-regulating process seeks a steady state. On the left, you see an example of a self-regulating process. In the self-regulating process, when the controller output is stepped, the process variable responds and steadies out at a new value. When the controller output is stepped back to the starting value, the process variable returns to that initial value as well. Most of the loops that you will be tuning with are self-regulating. This includes such processes as flow, most temperature loops, and pressure loops, all fall within the self-regulating category. However, processes can also be integrating. In the figure on the right, you see an example of an integrating process. For the integrating process, when the controller output is stepped, the process variable does not seek a new steady state. Instead, stepping that controller output or moving it away from its balancing point causes the process variable to move in to ramp in one direction. When the controller output is stepped back to the starting value, that balancing point, the process variable now steadies out at a steady state that is different from the starting condition. The most common example of an integrating process that you're most likely to deal with in your facility is a level controller. Level controllers are all integrating processes. You may also see an integrating process in some slow temperature loops, such as a batch temperature controller. In order to describe the dynamics of a process, a first order plus dead time model can be used. As shown on the screen, the model describes the relationship between the process variable and the controller output. Within this model, there are three model parameters. The process gain, Kp, describes how far the process variable moves in response to a change in controller output. The process time constant, Tau-P, describes how fast the process variable responds. And finally, dead time, Theta-P, describes how much delay there is between when the controller output is changed and when the process variable responds. And we'll discuss each of these in a little bit more detail. So the process gain describes how far the process variable moves in response to a change in the controller output. In the example shown on the screen, a simple step test to the process was performed. This means that while the loop was in manual mode, the controller was stepped and the process variable responded. This test data can be used to calculate the process gain. Specifically, the process gain is the change in the process variable divided by the change in the controller output. So in this example, the controller output was stepped up by 10% and the process variable increased by 1 meter. The process gain is then 1 meter divided by 10%, which gives us 0.1 meters per percent. In this example, the process gain is positive. However, it is possible to have a negative process gain. In such processes where the process gain is negative, increasing the controller output would decrease the process variable. The time constant describes how fast the process variable responds. Specifically, it is the time that it takes for the process variable to reach about 63% of the total response. To determine the time constant, calculate the time difference between when the process variable starts to respond and the time that it takes the process variable to reach 63% of the total response. Your time constant will always be positive and have units of time. The process dead time describes how much delay there is between when the controller output is stepped and when the process variable starts to respond. To determine the dead time, calculate the difference in time between when the controller output is stepped and when the process variable starts to respond. So in the example shown on the screen, the controller output is stepped at 3.8 minutes. The process variable doesn't start to respond until 4.8 minutes, so that gives us a dead time of 0.3 minutes. So in order to determine these model parameters, a test must be performed. This test should be performed at the design level of operation that was previously established. Processes are non-linear. This means that they behave differently under different operating conditions. The idea of nonlinearity is illustrated on the image on the slide. In this example, identical controller output steps are performed. However, as the operating level changes, so too does the process variable response. At higher controller output values, the same change in the controller output causes a much larger change to the process variable. For this reason, it's important to perform your test and determine the model parameters at the level for which the loop will actually be operating. 4 popular open-loop bump tests are shown on the screen. These tests are all performed in manual mode. The step test is the simplest test and involves simply stepping the controller output. This is the test that we covered in previous slides to determine the model parameters. The pulse test is 2-step test performed in rapid succession. So instead of just moving the controller output once, you're now stepping it in one direction and then stepping it back to the initial starting state. The doublet test is 2 pulse tests performed in rapid succession. So in this test, you start with the controller output at the design level, you step the controller output above the design level, you then step the controller output below the design level, and finally return it to the starting value. This is the preferred test or recommended test since it captures data on both sides of the design level of operation, taking into account any nonlinearities in the process. Finally, the pseudo-random binary sequence test, or PRBS test, is a series of pulse tests identical in amplitude, random in duration. This test is used very infrequently, but has good application in certain processes that can't be bumped or stepped very far or long away from the design level of operation. So now that we have a good understanding of process dynamics and modeling, let's take a look at the PI controller. PI controllers use the algorithm listed on the screen. The controller calculates the controller output value as a function of the error in the process. The error is how far the process variable is from set point. Specifically, the controller output is calculated as a bias plus a proportional term plus an integral term. The proportional term adjusts the controller output to account for the error at that exact moment in time. The proportional term introduces our first tuning parameter, the controller gain, or KC, as it's listed in the equation. The value of the controller gain gives more or less weight to the proportional term. A larger controller gain will cause the controller to make larger, more aggressive changes to the controller output in response to any error in the process. A smaller controller gain will cause the controller to make smaller, more conservative changes in response to the error. The integral term adjusts the controller output to account for the integral of the error. The integral of the error is how far the process variable has been away from set point for how long. So the proportional term is looking at the error at that exact moment in time, while the integral term is looking into the past at how far the process variable has been away from set point and for how long. The integral term introduces the second tuning parameter, the controller reset time. The value of the reset time gives more or less weight to the integral term. Since the reset time is in the denominator, a larger reset time gives the term less influence, and a smaller reset time gives the integral term more influence. There are some rules of thumb that can be used as a first guess for guess and test tuning, as you'll see on the screen. These first guess or rules of thumb differ depending on the process and the speed of the process. Note that there's a range provided for each tuning parameter, making it difficult to find optimum tuning parameters simply through guess and test. Guess and test tuning is also difficult because there are two tuning parameters that work together to impact the performance of the control loop. Starting with the base case in the middle of the tuning of the diagram on the screen, if you move up a row, increasing the proportional influence, you can see that oscillations are introduced into the process. The increased proportional gain gives a more aggressive response to the error, introducing these oscillations into the process. Now look to the left of the base case, where the integral term is now increased. Notice that this also introduces oscillations. Since both increasing the proportional and the integral influence can cause oscillations, it's difficult to determine which parameter is causing the undesirable behavior when you're using guess and test tuning. Due to the difficulties with guess and test tuning, it is always a good idea to use the tuning correlations to calculate tuning parameter values. Control Station's LoopPro Tuner software uses the IMC tuning correlations. These IMC tuning correlations, when you're using them for tuning, you must first determine a closed loop time constant. The closed loop time constant describes how long it takes for the process variable to reach 63% of the response to a set point step. So this describes the desired speed of the process running in automatic mode. So a small closed loop time constant is going to give a fast, aggressive controller. A large closed loop time constant will give a slow, conservative controller. On the slide, there are some rules of thumb for determining the value of the closed loop time constant based upon the process time constant and the dead time that can be used to make your controller aggressive, moderate, or conservative. Once you have selected your closed loop time constant, the controller gain and reset time are calculated using the closed loop time constant and the model parameters. The value of the closed loop time constant is selected and is adjusted to make the controller more aggressive or conservatively tuned. Note that the more conservative the controller, the slower and the smoother the response. The more aggressive the controller, the faster the response, but the more likelihood for oscillation. So it's important to tune your controller as conservatively as the process will allow to minimize the oscillations in the process and minimize the wear and tear on the final control elements. So using all of the information that we've discussed in these slides, it is always important to follow a tuning recipe. This tuning recipe that we have outlined has 6 steps. The first step is to define the design level of operation and the control objective. This includes where the loop is operating, any major disturbances to the process, and the desired performance of the loop. Step 2 is to perform a bump test. This test should be performed at the design level established in Step 1 and should be performed using one of the tests listed on the screen, either the step, pulse, doublet, or pseudo-random binary sequence test. Once the bump test is performed, the third step is to fit a model to the process. The first order plus dead time model defines the process gain, time constant, and dead time, which tells you how far, how fast, and with how much delay the process variable responds to changes in the controller output. Once you have the model parameters along with the control objective are used to calculate the tuning parameters. The IMC correlation is used to compute these tuning parameters based upon a user-selected closed-loop time constant. Once you've selected the new tuning parameters, Step 5, you implement the new tuning parameters into the controller and test the performance. As we saw, PID controllers work off of error. So to test the new tuning parameters, error must be introduced into the process. The easiest or best way to do this is to implement the new tunings, place the controller in automatic, and perform a set point step. Watch the controller's response to the set point step to determine if the performance is acceptable. finally, if the performance is acceptable, you want to document the results. Documentation should include the loop that was tuned, who tuned the loop, when it was tuned, and the before and after tuning values. And with that, I believe we will now open it up to questions. Dennis, you wanted them to enter it into the dialog box, I believe?
Yes, thank you, Lindsay. Great presentation. We'll be happy to address any questions that today's session participants may have. Please use the WebEx text function to submit those questions. While we're waiting for one or more to be submitted, I'll just throw out a question. What is the benefit of using tuning software?
Tuning software really helps proceduralize the tuning recipe that we worked through. All of those steps are automatically included in the software, and you can automatically work through them as you're tuning the loop. Software also has the ability to handle more complex loops or data sets. It can handle oscillatory data, or if a loop has excessive noise, it's able to handle the noisy data. It can also handle more complex tests. In the slides, we calculated some model parameters by hand using a simple step test to generate model parameters from any of the other tests that we discussed that are more complex. The software would be needed since they would not be able to be calculated by hand. You're also able to complete the tuning faster using fewer bumps.
We haven't received any questions from the audience yet, so I'll follow up with a second question. How do you perform a test if the process can't be put in manual?
So performing the test in manual is definitely the preferred approach. However, oftentimes placing the controller in manual is not possible, either for process reasons or the operators may be unwilling to place the controller in manual mode. If that's the case, the test can be performed in automatic mode. To perform the test in automatic mode, instead of stepping the controller output, you would instead step the set point and allow the controller to respond to the process. If you're testing in automatic mode, there are some things you want to keep in mind. First and most important is that the controller tuning values, the current values, must be aggressive enough that stepping the set point generates a sharp change in the controller output of at least 3 to 5%. You also want to make sure that whatever test you're performing is moving the process variable at least 3 to 5 times the random noise within the process variable signal. And again, if you're performing the test in automatic, you will need tuning software to be able to analyze the data and calculate the tuning parameters.
Well, one last question for you, Lindsay. During the presentation, you focused on generating or calculating model parameters based on a step test. What are, if there are any, the downsides to the step test?
So the step test, as we saw in the slides, you can analyze and generate and calculate new tuning, the model parameters by hand. However, you're only capturing data on one side of your design level of operation. As we touched on, processes are nonlinear. They're going to behave differently at different levels of operation. So it's important to capture data on both sides of your design level of operation. Doing that allows you to essentially account for any nonlinearities that there are in your process, which is why the doublet test is preferred, since you're stepping the controller output both above and below the design level.
Fantastic. Well, that takes into account all of the questions we had for today. So on behalf of Lindsay and myself, thank you all for sharing your time with us today. Please join us for future WebEx presentations on PID control and process optimization. We hope you have a wonderful day and appreciate your time. Thank you very much.